Greetings, this is Artie from Artifact Electronics. In this episode, we're going to look at some repairs that I've done recently and what happens if you don't pay attention to the facts. When the board is telling you, or almost telling you what's wrong with it, but you ignore those indications and you just surge ahead and try to do things the way that you've always done them. Our first case is this board. It's a dot matrix display driver board out of an Adams Family pinball. A friend of mine gave this to me or asked me to fix it. What's wrong with it is that some of the screens on the display are corrupted. Some work just fine, you can read text, but when you get into some more graphical displays, they mess up. Now I have made a repair very similar, if not identical to this, when I was working on a whitewater pinball of my own. And normally what it means is when the display is corrupted is that the RAM chip, it's a static RAM chip, 8K here, is bad. They do go bad quite frequently, so whatever supplier Williams bought their RAM chips from was making suspect chips. So I took this on and not worrying too much about what the problem was. It should be a simple chip swap. Now these things are difficult to bench test because the board itself is purely combinatorial. Gets all its clocks and data from the CPU board through these parallel connections over here. In order to bench test it, you have to bring in a CPU board and some of the other boards and the wiring harnesses, because the CPU board won't boot up if it doesn't see any other boards and stuff, and the only way you can really test it is inside the machine. But again, this seemed to be very straightforward, that the RAM chip was bad, so it looked like it was only a matter of changing the RAM chip. So it seemed pretty straightforward. I cut the old chip out. I had no interest in desoldering it because cutting the chip out by cutting each pin close to the body and then removing each of the pins on their own is usually easier on the board, and there's less of a chance of damaging traces over here. And I wasn't interested in the old chip. I was pretty sure that it was bad. I do socket chips that I replace. I use a socket like this with machined pins, and there's a bit of a discussion about that, the advantages and disadvantages of socketing chips, especially if you're in an environment like a pinball machine which gets shaken and jarred all the time. And if you socket the chip, there is a possibility of itself working loose. And depending on what sockets you use, even though the one I used, I'm not sure, I think, you know, even though it's gold-plated pins, the danger of galvanic corrosion is minimal, if even there at all. But I still like to put in sockets. Why? In case something gets messed up when you're replacing the chip. So what happened was I put the new socket in, I put a tested SRAM chip in it. I tested it in a machine and the display was completely gone. It was dark. It wouldn't show anything at all. So I said, okay, I put in a working RAM chip, and now that is uncovering a bunch of problems in this logic. So let's figure out, you know, what else went bad here, that just changing the chip made it not work at all. These things are a little bit difficult to bench test because this board is purely combinatorial, and it gets all its clocks and data through these parallel connectors from the CPU board. But you can't just bring the CPU board and wire a new harness for it just to connect it to this, because then the CPU board will complain about not finding other boards and not boot up. And in short, it's very inconvenient to bench test these. So you basically have to put it into the machine and contort your body to get in there and measure things. So my question was, what did I aggravate by changing the chip? I tested continuity between each pin to make sure that I hadn't shorted a pin when soldering this into place. But it all looked good. I put it in the machine, I used a logic probe on it, everything seemed to be working. The clocks were coming in, the data was coming in, but no dice, nothing was working. So the solution was obviously staring me in the face, but I did all the extra work of checking things, measuring the live board. Obviously I did something that broke the board when I changed the chip. So what I had to do is, I had a similar socket like this in there, and what I did was this. So after removing the chip, I went in and cut all these cross members with wire snips to end up with two SIP sockets, essentially, and started observing. Now remember, I did short checks between all the pins, and those were all good. But once I had better visibility in here, and that's going to be absolutely impossible to show, but what I found was that there was another trace unrelated directly to the RAM chip, but the trace ran in between two pins and then went through a via somewhere else. And I was looking at it, it looked kind of funny. So basically at this point, without cutting apart this side, I carefully removed this side of the socket, because if something had gone wrong, obviously I did that when I cut the pins on the original chip, and one of the pins must have exerted force to do something to the traces. Long story short, I removed this side only, and it looked like one of the traces running between pins, and again, it wasn't connected to any pins on the RAM chip, but it was shorted to one of the data lines of the RAM chip. It was an easy fix to basically clean up that trace. There were bits and pieces of the pad for this chip that had been torn loose, and they were making a hairline connection to this trace that was coming from the underneath. I took it out, I put in just a SIP socket, 14 pins long, very carefully soldered it, and made sure afterwards of checking all the connections, buzzing them out, making sure that there were no shorts to signals that were just using this real estate to pass through. I put the RAM chip back in, put it in the machine, and it worked perfectly. So the moral of the story is, I spend a lot of time checking things like operation of the rest of the board and all of that, which was unnecessary. The solution was staring me in the face. I changed a part, and that made the problem worse. So obviously I did something wrong at that point, but I was being thick-headed about it and just following my normal diagnostic procedures, and thus wasted a lot of time on fixing this. So look at the history. What have you done to a board? It's the same as with writing software. If you change something and things down the line break, well, look at your recent changes, and at a minimum try to undo them. Try to get the board back to where it was before you repaired it. Now, I couldn't do that with this because I had destroyed the old chip, It would have been ideal if I had kept it, put the sockets in, and then put the chip in to see if it at least acted exactly the same way it acted before. But that's really it. So I messed up on the repair, and I should have just undone my repair and redone it and carefully looked. Another problem with sockets, of course, is when you have a socket like this, it kind of obscures what's going on underneath. So in cases like this, I more and more drift towards using SIP sockets that you cut to the proper length and put in, because they offer visibility, much more visibility of what exactly is going on here. And if you see anything suspicious, you can just take out the offending SIP socket, replace it, and then do some careful measuring. Now, using a SIP socket instead of a regular socket, and here's a strip of SIP sockets, does take a little bit longer, but it's definitely worth it. And the procedure really isn't that bad. You just cut length of this socket for the number of pins you need. You insert them loosely. Well, you just insert them in the holes that you cleaned out. But the important part is you take a chip, maybe from your chip graveyard or whatever, and you insert it. Insert it all the way, and then use a piece of tape to hold this whole assembly to the board. Then you turn it around. You solder 2 pins on it, on opposite corners, like this one and this one. Turn it back around, remove the tape, and make sure that the sockets are sitting flush with the board. But having put in this chip ensures that they are properly, that they're not bending out, that there's no angle, that they're perfectly parallel. And once you see that the SIP sockets are sitting properly on the board, resolder all of the, solder all of the other pins, don't forget to pull out the junk IC, and you're all done. And you have an environment where if things don't work, you have some visual access to your work to figure out what went wrong. The next problem child was this Atari Pinball CPU board, which had me chasing ghosts. The repair itself was relatively simple. If I remember correctly, the voltage regulator had gone bad. And also they used this power resistor over here, which originally was a ceramic, a 4 ohm 15 watt resistor. They use this, and I've talked about it in a previous episode where I fixed this. It's special because the regulator can only supply 3 amps and then goes into thermal shutdown. But the way they use this trick where they bypass the input to the output with a power resistor, and what that does is it actually lets more current pass through. You're dividing the current that flows directly through the regulator versus giving any extra current an extra path, and but the regulator will still regulate it at 5 volts. And if the board for some reason needs more than 3 amps, it still works, even though this thing gets smoking hot. But it works. I've looked at the original data book for the 323K, and it's in there. It's buried in there as an example circuit for how to get more current out of it. Looks a bit fishy to me, but hey, they made thousands of these boards, and I'm assuming most of them worked for a long time. But that was the only problem with it. It couldn't supply enough current. And, well, great. Then the board came up. One thing to note on this board is there are a lot of blue wires, jumpers, and these are factory mods, because if you look at them closely, they're pretty cleanly done. The wires are run underneath other chips, instead of just flopping around on the board. They're cut to the proper length. You don't have these huge loops sticking out over here. But there's a bunch of mods on here, and they usually relate to the timing. There's a watchdog on here, which is a really good idea, because if the processor jumps off its tracks, it may end up pulling in a bunch of solenoids and your playfield goes up in smoke. These boards always have problems with the watchdog circuitry, and from this factory mod, which I didn't even bother to figure out exactly, they're changing the timing of the watchdog timer for, well, whatever reason. But what I usually do on the Atari boards is the first 5 Atari machines, basically, well, with some exceptions, the boards were interchangeable. And you could just you'd burn EPROMs and make them, make the board run into one of 5 machines. And what I do is I test them. I go through my whole collection of EPROMs and make sure that the board, at least on the bench, boots up properly and displays stuff. And on this one it was very strange, because this board, if you look at the revision on the board, what is it, a dash 08, and it's also marked with AA over here, which makes it an Airborne Avengers board. So I tested it with Airborne Avenger EPROMs in these sockets, and everything worked fine. But then when I went to use any of the other ROMs I had, the board wouldn't boot up. And of course my first suspicion was these mods that had been made on this board. Maybe there's some specific mod they made for Airborne Avengers that wouldn't allow any of the other ROMs to run. I looked, I checked, yeah, it was basically dead. I mean, everything was running, but I guess the path to the EPROMs seemed to be interrupted. It almost looked like there were addresses shorted or data shorted, but that didn't make any sense, because if I put back the Airborne Avenger ROMs, it ran perfectly fine. And here's where the problem was. Here's another board that's still eluding repair, but it serves to illustrate the point or the mistake I made. As you can see, it's got these towering sockets over here. It's got 8 sockets for bipolar PROMs. Originally, this part of the board didn't exist on early revisions, so you were stuck with using the bipolar PROMs. On this one, everything's socketed, and you can either put in a set of 8 bipolar ROMs or put EPROMs in here. And it's pretty obvious. I mean, the industrial strength sockets they used here make that clear. You may already guess what I completely overlooked on the other board. It actually has bipolar PROMs. But, I was blinded. I kept looking. They were just there. It just looked like the rest of the board. There weren't any towering sockets over here. But the whole problem was, it already had ROMs in there, and I was putting in a second set of ROMs. Well, how come it worked with the Airborne Avenger? That's because the EPROMs contained the exact same code that the PROMs contain. So when it started reading from them, yes, it activated both of them at the same time, but the data coming out of them was identical. So the data didn't get corrupted, the processor could read it, and it went along its merry way. But of course, when I put in a different set of EPROMs that had different code in here than in these bipolar ones, Well, when they both got enabled simultaneously, there was data bus contention because the data coming out of these and the data coming out of these was different. And so it couldn't run because the code was getting corrupted completely. So obviously I put a little note to self in here. Don't put anything in here because these things are soldered in. I mean, why would you put sockets here if you got the other ROMs soldered in? I don't know, but yes, I assume responsibility for that stupidity and sitting there for an hour or two trying to figure out why it would only run with one specific set of ROMs. So what do we learn from this? Open your eyes, look at the board. And in my case, it's definitely not excusable since I have a bunch of these boards and I've looked at them a lot of times. But hey, here was a clear indicator. And I mean, if both are socketed, yeah, great, that makes sense, either or. But if one set of ROMs is soldered in, there is no either or, and they should not have put in these sockets. But keep your eyes open, and you will save a lot of time chasing your tail. Case number 3. Always check the entire setup. You may fix something on its own, but whatever error there is may be caused by an external element in your chain. So this is a rack mount hybrid synthesizer. Doesn't have a keyboard, so I mean you can't play this thing without some sort of a keyboard. I have a small keyboard that has a MIDI output that gets plugged into the back of this, and you use this to play this. So we turn it on. So it comes up, and the display, consisting of 3 7-segment displays, it actually conveys the data very well, but you can use the up-down buttons to go to different presets. And the way this instrument works is in order to edit things, which you use these 6 knobs, and it's not a very intuitive way of doing it, and it's somewhat error prone, and it's always live. So you have a preset. Now if I turn any of these knobs, let's say I turn this one or this one, it says cutoff mod in this line because when you do a mode change, the LED tells you which row of writing to look at, and that'll tell you what a particular knob does. So we were back over here. It says volume. There's some of them have 2 different functions, and those are accessed by pressing the shift key. And anyway, it shows you that editing patches on this thing is not a whole lot of fun. Now these are live all the time, so you have a patch and you want to change, as we set the volume over here. All you got to do is turn this button here and it changes the volume of the patch. So you can go from 127 down to 0, and that's part of the patch. And that's great. So what happens now is we have actually changed the parameter of the patch. So if we go back and we look at that patch, it was patch 4, but instead of saying P4, it now says E4. And what that means is you edited the patch. You changed it. And you can undo that. It's not a big deal. But the complaint on this one was that, let's say you select a patch and you let it sit for a while, And when I come back and look at it after 20 minutes or so, instead of saying P7, for instance, it would just say E7, which means these knobs decided to move on their own. Well, the knobs don't move on their own, but they are potentiometers, and potentiometer jitter was a very likely source of that happening. So I embarked upon taking this thing apart, removing the pots, and basically they were sealed pots. I had to take them apart to get inside to clean them. Well, they were sealed. They were they were pretty clean inside, but I went ahead and cleaned them up with contact cleaner, put it all back together. It took me a while, and then let it sit to make sure that it wasn't pot jitter that was basically going into auto edit mode on this thing. And I let it sit for a while. I come back and I am greeted with another E on whatever patch I left it at. Now, one hint from that was that, remember, when you turn knobs, it actually shows you what the parameter is. Whereas in this case, when I came back to look at it, there weren't numbers in here. It was just saying this has been edited. Aha. So that means that I was wrong. It wasn't the pots doing it, because if the pots were jittery and they did something, when I came back to the room, I should see something like this on the screen. So if you move the pot, it shows you what that pot, what the parameter of that pot is. Yet, all I saw was this. So it had to be influenced by an external source. So it was telling me what was wrong with it, i.e., there was nothing wrong with it. Here's the culprit. So this is a trash-picked MIDI controller board. You know, can't let anybody throw away a good keyboard just because the USB connector on the back is a little bit bent out of shape and there's pizza sauce all over it. But this was a culprit in that, or maybe it's the cable, the MIDI cable, but it was extremely noisy, and it actually kept sending data on its own. Now, the way these things work is you can remotely turn these buttons. Well, you're not remotely turning the buttons, but you can basically send the proper MIDI command to change a parameter of the current patch that you're looking at. And when you do that, you won't get any numbers on here. It will just change the P to an E, saying, hey, something in this patch got changed. And the only one who can change it is if this keyboard is connected and it's on. And generally it was on and it was connected because I kept testing it to make sure that, you know, things were still working. So the final test was disconnect that keyboard or power it down, select the patch, go away, come back the next morning, and the P had not turned, had not morphed into an E anymore. So the whole problem was that this was either glitching or deciding to send garbage every so often. And yes, I could ascertain that by putting a MIDI monitor on this thing and letting it run for a while and all that. But that's not really, that wasn't really what I was interested in. I was interested in fixing this, and it didn't need to be fixed, even though it's got the cleanest pots in the world. I mean, it's an early 2000s instrument, so, you know, it's been around for a while. But the point being, always look at every element in your setup, because the device that is generating a complaint is not necessarily to blame. And for our last case, always check your work before putting the device back together again. So in this case, we have something that happens quite commonly. Here's a MIDI connector. This board is just for illustration purposes. This is not the actual board, but you have a part that gets stressed by inserting cables. It could also be a pod, a PC board mounted pod or button or whatever. And the stresses, what they will usually do is they can cause the solder joints to break or crack. So this is where the pin is coming through from this connector, and it goes and connects itself somewhere else. But if you keep putting stress on this connector, eventually it can crack the solder joint. And the fix for that is very simple. You reheat the connection, add some new solder to it, and you're good. But the situation I ran into was a little bit different, and I'm going to have to show that on a whiteboard. So we have a pad. That's something that is mounted, a control mounted on the PCB itself. One of the pins is sticking through here. And then we have a trace that goes from here and, say, connects to some other pad over here. Now what happens is, this is a stressed connection, and normally when it gets stressed too much, as mentioned before, the actual solder joint may crack, and all you got to do is simply reheat it, reflow it with a little bit of solder, and you're good. But what can also happen is that the trace that's supposed to connect to the pad actually develops a break right here, so that this pad is no longer connected to this trace. And that's usually easy to see. If you're suspecting something isn't connecting properly, remove the solder from this joint and just observe things. And cracks like this will show up real easily. And the best way to fix this is to take, like an X-Acto knife, and scrape the solder mask off of the trace over here, and then just put a blob of solder that extends from the pin to the trace, and you got the problem fixed. Well, that's the situation I was in, and that's exactly what I did. Cleaned out the solder, removed the solder mask here, and scraped it clean so the copper was showing, and then laid a nice bead of solder across these two. So the connection was made again. Being very sure of my fix, I put the whole damn thing together again, and unfortunately there were lots of screws involved, and I went through one revision where I ended up with 2 screws that weren't used, and I had to tear it apart again to find where I had missed putting back those screws, and I put it back together and it didn't work. And in that particular case, this was the center pin of a pot, and what it did was there was a blinking LED that did some for a low frequency oscillator, and when you turned the pot, the voltage changed that the center tap gave you, and it changed the blink rate. So it was really easy to look at, but the device was rebuilt, and the pot had no effect on the blink rate. As a matter of fact, the LED was just on solid. So of course I tore it apart again and did what I should have done from the very beginning. After applying my fix, you buzz out this connection. Do you have continuity between these two? And lo and behold, there was no continuity. So for some reason, the solder didn't adhere properly to the trace that I had scraped clean, or I thought I had scraped clean, and so the defect hadn't been changed at all. It was the same as before. We had a cracked connection here. In a case like that, what you do, A, is you get some thin gauge wire because signal's coming off a pot. You don't want this fat cable running here. And you basically go from this solder connection to this one. You solder this here, this wire here and here. And now for the most important part, you buzz out the connection. Is there a connection between this pin and this pin? And you don't measure it at the wire that you just inserted, but rather another part of the pad, and the same here, and make sure that you're as close to 0 ohms as possible. Needless to say, that fixed it. Second thing I did wrong is when you fix something, test it. Don't put it back together again. Don't be overconfident. Put it on the bench, test it. This one was really easy. Apply power to it, and when turning the pot, the blinking frequency of the LED should change, and it worked perfectly. And once I put it all back together and actually listened to it, yes, it was a fix. But save yourself a lot of time and properly test your work before putting a device back together again. When repairing one of these beauties, don't overlook anything. Look at the clues, the board, or the operation or lack of operation of the board. The clues that you're given, and follow those clues. They mean something, as the last 4 examples I showed you should prove. And you will end up with more economical, time economical repairs. But you know, time is what usually most people overlook. It's not the parts you replace, it's the amount of time you spend on diagnosing and fixing a problem. And check your work at every step. Meaning, if you just fix the connection, actually buzz out the connection. Don't measure the wire itself you use to change the connection, but measure it at different points of the solder, at the 2 points that are supposed to be connected. Then, if possible, and this is not always possible, but in most cases is, power up the thing and test your fix. Then, of course, once the fix seems to work on the bench with the bare PCB, put it all back together again and check it in actual operation to make 100% sure that you got the error. Thanks for watching. Please like and subscribe. Give me a comment. Tell me about your repair experiences where you did something wrong that cost you some time, if not a lot of time. And we'll see you next time. Bye.